So we want to evaluate the limits. You guys asked me to do part B. So we're taking the limit of the vector valued function. I put it in IJK form. First component, e to the negative t. Second component, arctangent. Do you know what that means? Arctangent is tangent inverse, right? Same, that's arctangent of, and then put t. Okay. And then the other one's just a rational function, 2t squared plus t plus 1 divided by t squared minus 3. So we learned last time that last week anyway, you can take the limits component by component, right? So I'll write this out, although I'm not going to require you guys to do that. This would be equal to the limit as t goes to infinity individually of e to the negative t, and then i's, because e to the negative t, limit of e to the negative t as t goes to infinity is going to be the I component. The limit as t goes to infinity of the arctangent of t, j, and then plus the limit of that rational function. So what's the limit of e to the negative t? 0, right? If it helps, picture a graph of it. So if you just graphed in the, I guess the input's t, so it'd be the t f of t plane or t x of t plane, I guess, since it's the first component x of t. Then that graphs to be, well, e to the t, x of t equals e to the t would graph to look like that, right? But what does the negative do? Kind of turns it around, right? And you can see that as t goes to infinity, then the graph of x of t equals e to the negative t is going to approach a height of 0. That's how you remember it anyway, because you really should have those kinds of graphs in your head. Those, so a basic library of graphs should be in your head. Like, what does the arctangent look like? I'll draw a graph of that in a second. What do the basic trig functions look like when you graph them? All those should be in your head by now. If they're not, it's okay. Just get them there, right? So this one's right away, 0i, which you don't even need to write down. What about the limit of the arctangent or tangent inverse as t goes to infinity? It has an asymptote, and that it approaches as t goes to infinity. It's pi over 2. So if I were going to draw a picture of that, let me erase this one. And if you need reminding of what it looks like, you can always graph these two-dimensional guys in your calculator, right? So it actually has 2 asymptotes. We'll put them in red, I guess, and then make a copy of that. So if this is the t-axis, I suppose this would be the y of t-axis. And so this would be y equals pi over 2, right? This asymptote? This asymptote would be y equals negative pi over 2. And do you remember what the tangent looks like? It kind of wiggles in the middle, approaches the asymptotes as it goes to the left and right, respectively. And it'll approach, as t goes to the right, it'll approach a height of pi over 2. Not necessary to draw this. Don't get the wrong idea. This is just a known, this is a known limit. You might have forgotten it because it's been a couple semesters since you took Calc 1. But you can just go right to the answer. Not necessary to draw that. So we get, for the j component, just pi halves. And then how would you approach this, the limit of the 2t squared plus t plus 1, all divided by t squared minus 3? You could definitely use L'Hopital's rule. So there's more than one way to do it, right? Yeah. If we use L'Hopital's rule, I think we're going to have to use it a couple times, right? So the limit as t goes to infinity, if you apply, put a little h above here to show that that's what you did, so that I know that you know what you did. What would you get here? 4t plus 1 over 2t. And then, oh, we'd have to do it again. So we could leave this guy out. Pi over 2j plus the limit t goes to infinity of L'Hopital's rule again. What do you get? Ooh, I think I can do that one. I don't know. It's pretty hard. And then that's times, what was it, k? Yeah, it should have been k on the end.
So
Fix that.
will you accept like an answer if we do the shortcut?
Hold on just a second. Let's finish up the idea here. So pi halves j plus 2k. Would you buy that? Okay. What shortcut are you referring to?
The coefficient shortcut, where the leading coefficient.
So this is something that I teach my pre-calculus students. If the degrees are the same, it's got to be a rational function. The degrees are the same, then the limit's just going to be the ratio of the leading coefficients. Yeah, that's true. Let me say this: be able to do it either way. Okay. Just to give myself a little flexibility there.
And if we do it in component form instead of IJK?
That's fine. But as a general rule, so that just because I remember I was afraid of IJK form when I was first introduced to it in Calc 3. If you start off in IJK form, just for your own benefit, I would stick with IJK form. And then if you start off in component form, in general, not every time, stick with a component form. If you can't, when it's practical to do so. Sometimes, and you'll see me do this, in certain situations, I'll switch to component form because it is a better form for certain things. Here it doesn't really matter, but. Sure. So everybody's good on that one? Let me erase this stuff so I can keep everything in the same picture. Okay, so let's just take the limits. I'm going to do this. I'm not going to show as many steps on this one. What's going to be the limit of the sine of t as t goes to 0? Direct substitution, right? Sine of 0. So the work I'll show is I'm directly substituting 0 in. That's the only work I'm going to show. And then in the next step, I'll write down 0 in that spot. What about that other guy? Good old L'Hopital's rule. So by L'Hopital's rule, you could say that it's the limit. If there's an intermediate step in L'Hopital's rule, you have to keep the limit notation. Limit as t goes to infinity. What's the derivative of the top? Negative e to the t. Derivative of the bottom? 1. And then that guy's good to go. And then this guy. Ooh. Well, you better check it. If you directly substitute in 0, we do get 0 over 0, so you could use L'Hopital's rule. You could also try multiplying numerator and denominator by the conjugate. What happens if we directly substitute 0? That doesn't work, yeah. So which way would be easier? Conjugate? Did you already try it? Okay. So I would maybe do this as separate scratch work here. So I would, because it's going to be a mess to try and keep all the vector notation together. So just to remind you of a trick from Calc 1, we could multiply the numerator and denominator of this thing by the conjugate of the numerator. Let's see if that works. It's just when you have a number plus or minus a square root, it's just a trick to try. You don't necessarily know for sure if it's going to work. So we're multiplying by 1 in the form of the conjugate of the numerator. 2 plus square root of t plus 4 divided by the same thing. And that's a trick worth talking about, I think. And so then what's that going to equal? Well, don't lose your limit notation. Keep the notation. Don't get lazy. Keep the notation. And then on the bottom, I'm going to leave the bottom as just 6t. I'm not going to multiply it out yet. 6t times 2 plus square root of t plus 4. If I need to, I'll multiply it out later. Is that okay? And then what happens when I multiply conjugates together, the stuff on top? 4, this is the only time from the FOIL method you don't have to worry about the outer and inner terms, right? So 4 minus what? 4 minus t plus 4, and then you can see something nice happening here. You end up with 4, okay, distribute this, you get negative t minus 4. The 4's cancel, and you get just what? Negative t on top over 6t, and you can see what that trick does for us now. It allows us to divide out the offending factor, right? And so now I think you can hopefully see that we get negative 1 on top over 6 times the quantity of 2 plus radical t plus 4. On the bottom, I think there's no issues with plugging in 0 now, direct substitution, right? Beautiful. And then we get, I'm saying beautiful, it's a problem I wrote. Beautiful. I haven't done it in a while. I'm not patting myself on the back, I just think it's a nice problem. Most of the problems are based on Stewart problems. I just changed the numbers so I don't get somebody telling me to take it down or you'll have copyright infringement or something. Probably wouldn't happen anyway. But so anyway, what do we get on the bottom? 6, plug in 0. What do you get here if you plug in 0 there? So square root of 4 is 2 plus 2. So negative 1/24. Did I do that right? Everybody agree with that? Okay, but wait. We got to put that somewhere. Where do we have to put that? Right there. And then I didn't leave myself any room, did I? Shame on me. So let me do this. So that just leave the scratch work somewhere else and then write the final answer. Sine of 0 is 0. What did we decide this limit was? You can directly substitute 0, so what do you get? Negative 1, and then negative 1/24.